Here's the story of Mr. Wade's evolution. I taught mathematics at this institution, but then came March. They postponed school. COVID-19 was playing us like a fool. I snuck back in and taught some AP, but they locked up the building and cut the AC. I got frustrated and wrote some sick rhymes. I filmed a rap video just to pass time. I started teaching lessons from my house in Brentwood. Oh wait, you're not supposed to see my real house. I started teaching lessons from my house far away, but I missed writing on a board every day. I talked to my friend Steve Smith, computer hacker. We had to find a whiteboard and he's no slacker. We looked around the city, we finally scored, and now I'm back teaching from a dry erase board. Now we're off Schoology, every single grade, and that's the story of the evolution of Wade.
And now, AB 3-2. So, first of all, we want to talk about what is slope measuring. Okay, 3 things that the slope measures. What was the whole theme of 3-1? Wasn't it tangent slope, right? So, slope is one thing the derivative measures in real life. Slope of a roller coaster, slope of a road, slope of a driveway. Okay, second, what else does the derivative measure? Think about the possum problem that we did before. Didn't it measure the rate that the population was growing, or the rabbit population we did as well? Rabbits, possums, all kinds of things, okay? Cockroaches, integrated 3. So, rate, okay? Or either growth rate or rate of decay. It's going to be one or the other, right? All right, so rate that something is changing, rate that the possum population is changing. Now, 3 things. There's one we haven't talked about yet. We won't really get into it until the second semester, but we do kind of hint at it just a little bit today. The third thing that the derivative measures is also the velocity, which we will kind of loosely debut today, all right? So we have an example from the Pennsylvania Turnpike, and this is a really fascinating real-life example. The Pennsylvania Turnpike goes all the way across Pennsylvania. I've driven on that many, many times, and it's a toll road. You know how we have these nice free interstates in Tennessee, but some of you have probably been on a road trip where you had to go through a toll booth, you had to get a ticket, and then when you exit the turnpike later, you've got to give them the ticket, and depending on how many miles you've been on the road, they charge you a certain amount of money, right? Oh, you were only on our interstate for, a couple of miles, all right? Give me 35 cents, right? Oh, you were on our turnpike all the way across Pennsylvania. Okay, give me $10.26 or whatever it is these days. Okay, so they're going to charge you the longer you're on the toll road. So the Pennsylvania Turnpike is Interstate 76, but it's I-76 / Pennsylvania Turnpike, and turnpikes cost money. All right, so what happens is this. Let's say that we got on the interstate. Notice that X is hours and Y is in miles. So X is hours. We have the coordinate 0, 2. See 0, 2 right here and here? At time 0, they punched your ticket, and sometimes it's just an automatic toll booth, and sometimes it's a human being, but they punched your ticket, and you are at mile marker 2. You've been on the interstate and seen the mile markers before, right? So you're at mile marker 2. You're kind of at the beginning of the turnpike. You're only 2 miles into the turnpike when you basically took the on-ramp, all right? So there you are at time 0. Now, 3 hours later, you are at mile marker 242, which means you've traveled 242 miles now. But have you traveled 242 miles? No, because you got on at mile marker 2. So you've actually traveled 242 minus 2 total miles. Now they can charge you for however long you've been on the interstate, okay? Now, here's the thing though. This is mapping out where you were. This is your location throughout. When the curve is kind of shallow, think about tangent lines. Aren't tangent lines derivatives? And their slopes are derivatives? But didn't we just discuss that they're also velocities? So if your tangent line is rather level and kind of shallow, you're not going very fast. You see right here in the middle of this shape though? You see this tangent line? You see how steep it gets right in there? The steeper your tangent line, the stronger your slope or derivative or velocity. So the car is going very fast when your tangent line is very steep. There's a real life connection. Now here's the thing. If you get onto I-65 out here near NSA, guess what happens? Well, they can't tell you when you got on the interstate, and they can't tell when you got off the interstate, unless there's a police officer sitting on the side clocking you by radar, okay? But that's happened to my friend Steve Smith a few times. Not me, but Steve Smith. But guess what happens on a toll road? You have to enter through a booth and you have to exit through a booth. That ticket knows and can tell the computer how long it took you to get from point A to point B. Is anybody catching my drift here? Are you following what's going to happen? In real life, this is true. When you stamp that ticket and you leave the interstate, it knows your average velocity throughout. And if your average velocity is too high, the person at the toll booth taking your ticket, they don't know, they're just there to run the cash register. But the computer logs it and knows if you are going too fast on average, and they will send you a ticket in the mail automatically. It happened to me, my friend Steve Smith. And to calculate that, you see right here, this is what the computer does. Average rate of change. Heck, we had that phrase in integrated 2 and integrated 3. That goes way back. It's not even a calculus problem. It's an integrated problem in disguise. So if you do the average rate of change, now, if you just do the rate of change, remember, rate means take a derivative. We will do rate problems this year where you take a derivative. But if it says average rate of change, it's straight out of the integrated classes. It's the old middle school slope, y2 minus y1 over x2 minus x1. Okay, that's all it is. A middle school problem hiding in a calculus class. Okay, so rate is derivative for the future. Average rate is just middle school and integrated 3, rise over run. Okay, they're going to give us here, I've given you the interval from 0 to 3. That's x1 and x2. That's a time frame. You were on this interstate from time 0 to time 3. So x1 is 0, x2 is 3. We need a y1 and a y2. Well, that's mentioned over here. At time 0, you were at mile marker 2. At 3 hours later, you were at mile marker 242. Does the computer say too fast, or does the computer say, you're okay? Well, let's see. The average rate of change. We were just doing this in my integrated 3 class, actually. First chapter. 242 minus 2, y2 minus y1, over x2 minus x1. That's 240 over 3. It's our old favorite game called Hide the Zero. 24 over 3 is 8. Now put the 0 back on. Uh-oh. The person at the toll booth takes your money and they don't know, but the computer knows you averaged 80 watts. I'm sure you're all thinking, since this is a real life problem, miles per hour. Well, you're right, but why? Okay, slope, average rate of change from integrated, is y's over x's, right? Rise over run. Okay, the y's were miles, so the top is miles. Okay, this is basically, let's put it here even. You went 240 miles. The bottom would be the x's, which are hours. So you went 240 miles in 3 hours. Didn't we learn in integrated classes that the division sign is also per? It's the word per. You went 240 miles per 3 hours. So if you always put your y units over your x units from the words I actually give you, y words over x words, you're going to get the units right every time. It is miles per hour, and that's why, because it's rise over run, y over x. So that is 80 miles per hour, and that was your average. You were doing better when your tangent slope wasn't so steep. In here, you were really flying, and then you got nervous and you slowed down because there are police patrolling this. But in the end, you thought you can get away with it. You couldn't. You were speeding on average. And that's how they use calculus and even middle school math to bust you on the Pennsylvania Turnpike. True story. All right, letter B, more real life mathematics. Okay, so you've got a mole on your skin, all right? Moles sometimes grow, but if they grow too fast, they're dangerous and probably cancerous. If they grow slowly or normally like a mole sometimes does, it's not that bad. This can happen to freckles. This can happen to random red spots. I'm specifically thinking about my arms because I've probably told you stories in class already in the past that, let me tell you, Mr. Wade, my mortal enemy is the sun. I can walk outside and I can get sunburned on a cloudy day in like 10 minutes unless I have on SPF 50 plus. It's not even fair. I have the palest skin in the universe, all right? Some of you out there are with me. Most of you probably aren't because most of you can get tan. I can't. So I've had so many of these mysterious spots frozen off my arms over the years. Let me tell you, I just hope it doesn't get in my system because once it gets in your system, you're in trouble, all right? So this is what happens. This is the equation for a mole that they're studying on somebody's skin, and it seems to be growing. Okay, I don't really get the moles. I just get these random cancerous red spots, but they always catch them in time. So let's say somebody has a mole, and the equation is 0.5 cube root of x minus 7 plus 3. All right, I did some research in real life. I noticed that a lot of these growths actually go with cube roots. Interesting, sideways snake. Okay, now find the average rate of change. All right, rate derivative. Average rate of change, just the old integrated classes. y2 minus y1 over x2 minus x1. But a real life scary situation. Okay, 8th month. We only want to look at the 8th month. Is it growing too quickly this past month here? This is the 8th month we've been studying your skin and we don't like what we see. Or maybe it's safe. All right, let's try it. Now, last time, remember on the Pennsylvania Turnpike, I gave you an interval from 0 to 3. I have not given you an interval this time. You create your own interval, all right? How do you frame the 8th month? Is that like 0 to 8? Is it 7 to 8? Is it 8 to 9? Like, what is it? Let's think about it logically, okay? If you were only looking at the first month and you were studying this thing on my skin and you're like, yeah, well, you need to come back in a few months so we can check it again. The first month is, it starts at time 0. Let's start the stopwatch, okay? Time 0, and it ends at the end of the first month. So the first month is 0 to 1, okay? The second month of a study, of any kind of scientific study that you can think of, the second month would be 1 to 2. You see, it's the end of 1 month has been completed to the end of 2 months have been completed. That's how you set up an interval. So the 8th month, don't do 0 to 8 because that would encompass 8 months. We're only trying to get 1 month. It happens to be called the 8th, but it is only 1 month. Okay, according to the pattern, do you see that the month number actually goes last? So the 8 would actually go last. And if you want to frame only 1 month, wouldn't it be the end of 7 months completed to the end of 8 months completed? That's how you frame just the 8th month, so 7 to 8, okay? So my x1 is 7, and my x2 is 8, because x is in months, and time is always related to x, right? Now, we need y coordinates. Okay, we need a y1 and a y2. Heck, we were just doing this today in my integrated 3 class just this morning, all right? y2 and y1, I didn't give you y's, I did last time, but can't you take the x's you just discovered and plug them into the given equation to create your own y's? Original function. So y1 would be, take 7, plug it in there, and you'll get 0.5 cube root of 7 minus 7 becomes 0, cube root of 0, plus 3. Okay, any root of 0 is 0. 0 times this is also 0, plus 3 is 3. All right, there's your outcome. What are the y's? Just out of curiosity. Oh, that's millimeters. Okay, these moles can be very tiny but still dangerous. So this measures 3 millimeters. Now, at the end of the 8th month, you came back for your checkup. You take 8, you plug it in this equation, and you get 0.5 cube root of 8 minus 7 is 1, and then the plus 3. Any root of 1 is always 1. 1 times 0.5 is 0.5. 0.5 plus 3 is 3.5. So that means at the end of the 8th month, this thing is 3.5 millimeters. I wonder if that's normal in the world of dermatology, or is that abnormal and too fast? All right, average rate of change. This is the average growth rate over time. Just like your average speed on the interstate over there, it wasn't your instantaneous speed, it was kind of an average over time. So m equals y2, 3.5, minus y1, 3, over x2, 8, minus x1, 7. You see how there's a 1 on the bottom? That's because we're only looking at something per 1 month, right? Just the 8th month. That should happen, okay? So it's over 1, or you could just drop it. 3.5 minus 3 is 0.5. And 0.5 over 1 is itself. So your final answer is 0.5. Now, 0.5 what's? You're going to want to put units on these answers in calculus. Okay, so remember, slope is y's over x's. The y's were millimeters. Over the x's were months. So very obviously, it's millimeters over month, which we call millimeters per month. Okay? Now I'm curious as a cat. Probably one of my friends call me Whiskers, I guess. So I asked my dermatologist. I unfortunately have to visit all too frequently to get these things frozen off my arm. So I asked the dermatologist, what's dangerous? What do you actually look at in your profession? And they told me real life math. If it's higher than 0.43, that could be dangerous. Very high chance of being dangerous, okay? This was 0.5 on this particular person. They need to have that thing removed because otherwise it's going to cause trouble, all right? And once the cancer gets in your bloodstream, you got a very low chance of coming back from it, so that's not good. But you can remove it and avoid that. One I had taken off, well, it was a red spot, not a mole, but one that I had frozen off last year was a 0.6, even worse than the cutoff and this particular person right here. No pun intended with the cutoff, all right? So 0.6, right, way above what the standard is that they look for. And thank goodness they got rid of it and I was cancer-free. That's a good thing, okay? Real life stuff, my friends, it's serious. All right, problem C is a real-life piecewise function. You can see the curly brackets there. It's a real story. I may have even done it in some of your Integrated 3 classes. It's out at 7530 Dairy Ranch Road, a real house out in Colorado Springs. You can look it up on Google Maps, actually. And what we're going to do is we're going to see how they build these roads and how they build these driveways in real life. So this was a really steep mountainous area because, of course, Colorado is very steep. And so what you have is you've got the city street is down here, right? And then you have a very steep driveway up to this house that's up here. Great house, Mr. Wade. All right. Now, how do you segue between a street, like cars are going this way, and a steep driveway? You can't just make it a straight line. If you have a street and a steep driveway and it goes to a crooked fit, you're not going to be able to drive up that driveway, right? So what they have to do is build a very flat parabola as a connector right in here. There's a very small parabolic portion. So picture a parabola like really flattened. That parabola will transition into the straight line part of your driveway. Okay, ax squared, that's the parabolic part, right? Ax squared. Bx plus c kind of looks like y equals mx plus b. That's the linear part of the driveway, all right? And they're going to fit together at 11, which was 11 feet this way. Now, I actually looked up real data on this place, on this house, and I actually constructed for us a real-life piecewise function to model this driveway. The problem is they built it way too steep, way beyond codes, and they had to redo the whole thing, and actually the engineering company ended up going out of business from all the lawsuits. It was a big mess, all right? So, first thing we have to do is find the equation of the parabola. Now, a wise man once said, plug in the phase change and you can pretty much set yourself up to solve any piecewise function. Remember that? That was Mr. Wade. Okay, phase change is 11. If you plug in 11 into the curve, you'll get 11 squared, which is 121a. Too bad we don't know what a is, all right? If you plug in 11 here for x, you'll get 11b plus c. Ooh, really too bad we don't know what b and c are. That's two unknowns. That's going to be harder to solve. This one's going to be a little bit easier. Okay, one extra twist we have not seen yet. The point at which the parabola joins the line is already labeled for you. So the outcome at 11 for both the parabola and the line is 2.2. So actually, both of these y coordinates should come out to be 2.2. And that's the first time we've had that information, all right? So this one's solvable, this one's not. Let's go to the first question over here. All right, so if you're designing this driveway, do the parabola first. The parabolic portion would be y equals ax squared for all we know right now. D of x, we'll just call it y. So that's the parabola part. Write its actual equation. Oh, we better find out what a is. Now, wait a minute. We plugged in the phase change. 121a happens to equal 2.2 where they're supposed to meet up. You don't want the curve and the line to be disjoint because that'll be a horrible driveway, right? So we know that 121a equals 2.2. Okay, divide both sides by 121. Just like an integrated 3 class with Mr. Wade, challenge yourself not to use a calculator and to do mental math. It's our old favorite game called Scoot because you can't leave a decimal in a fraction. So we're going to scoot the decimal, and it's actually 22 over 1,210. Okay, try to reduce it if you can. I do know that 2 goes into both of these because they're even, but even better, I do know that 11 goes into 22. I wonder if 11 goes into this number. Let's hide the 0. Hey, wait a minute. 11 goes into 121. You could actually take an 11 out and reduce like a pro. 22 divided by 11 is 2. And let's hide the 0. 121 divided by 11 is also 11. Put the 0 back on. 110. And now they're both even, so let's cut them in half. So the final answer is 1 over half of 110 is 55. And your final equation for this parabola, let's replace a with what we just found out. Y equals 1 over 55x squared. Didn't even really use calculus. We just kind of used basic math. Kind of middle school math / knowing how to handle a piecewise function. Now remember I said it had to be a really squished parabola? If it were the typical x squared, nobody's going to drive up that in a car. It's impossible. 1/55th means a shrink by 55. That's integrated 3. It's a parabola that's been crushed to 1/55th of its former self, so you can actually drive up the thing. So that little tiny fraction totally makes sense here. So now we go to the linear part of this driveway. So the linear equation is up here, the straight line part. Okay, the linear portion refers to d of x equals bx plus c, which I'll call y equals bx plus c. So this is the linear part. Now remember, with the phase change over here, 11b plus c equals 2.2. That's a dead end, no pun intended, because you know what? There are 2 unknowns. We don't know b, we don't know c. You can't solve that equation, okay? So that's a dead end there. And we didn't just find b or c just now, so we can't do it. So we have to be a little bit more clever this time, all right? So this is something that you couldn't even do in integrated 3 no matter how smart you are. And I know we got a class filled with integrated 3 superstars from the past. Well, this is the dream team, but guess what? You could not have done this problem until today in your lifetime. So here's the thing, all right? Notice what's so special about when you build a parabolic part of a driveway or a road, or like the road system and the road engineers that work in a city. The parabola that became the line. You can't have a crooked fit on a road or a driveway. It's got to be a smooth fit. Wait a minute. Do you know what happens when you extend the linear part of the driveway into this dashed line that I've drawn for you here? Does anybody realize that the line must be, keyword today, tangent? The line is tangent to the parabola part of the driveway. We're not seeing the rest of the parabola, but it's like that. Eventually it would go so steep that you couldn't even get up that road. So you can get up the parabola for so far, and then it smoothly transitions into a line. So that line is the tangent to the parabola. There's your breakthrough. Okay, so how would an actual road engineer do this in real life? All right, that's kind of a dead end. I mean, it's the right equation, but it's kind of a dead end right now. Isn't the derivative of the parabola able to give us the slope of the tangent line, right? Isn't that what the big theme today is? So, we just found the parabola. That's why I had you find it first. This is the parabola equation. If you take the derivative of the parabola, 2 comes down. 2 times 1 is 2 55ths. X to the first, drop it by 1. Okay? That's your parabola equation. Well, that's the slope at each point on the parabola, isn't it? The linear part of the driveway is at point of tangency, x equals 11. If you put 11 into the parabola's derivative, you will instantaneously get the slope of the tangent line at 11. How about that for a real life example, right? So y prime of 11 equals 2 over 55 times 11. Who sees the cross cancel? 11 over 55 is 1/5. And your final answer, 2 times 1 over 5 is 2/5. That's your final answer for the slope. But now what does it say? It says find the line's equation. We have to do one more thing. Well, first, let me unmark out this y equals mx plus b because we'll actually use it after all. That's a nice fancy camera trick there, isn't it, right? Okay, so now we know that the slope of the tangent line or linear part is equal to, what was it, 2/5. Isn't b currently representing the m position, right? That's the b right now, that's the slope. So y equals, put 2/5 in for the slope, x plus c. And actually, you could go find the c value now if you wanted to. Don't we have one coordinate on the line, 11, 2.2? You could plug in 11 for y, you could plug in 2.2 for x, and you could figure out what the c value is. We don't need to do that today. If you just leave it like that, that's fine, okay? But it tells you how to make the parabola segue into the straight line and have a valid driveway. Now, the engineers got the segue between the two correct. They got the point of tangency correct. Here's what they got wrong. They made the driveway way too steep. So this is going to answer the grade question. The slope of the linear part of the driveway is 2/5. We talked about grade in my integrated 3 class, actually. Here's a little refresher. Write this as a percent, okay? What is 2/5 of basically 100%? That's what you're looking at. I mean, there are lots of ways to do this, of course. Some of you can just look at this and tell me. If I wanted to get 5 to become 100 because all percents are out of 100, I could multiply it by 20 because 5 times 20 is 100. But what I do to the bottom, I have to do to the top. So 2 times 20 is also 40. So 2/5 unreduced is actually 40 out of 100. Oh, that's 40%, isn't it? And again, most of you can probably just look at 2/5 and tell me that, but that's a little helper there, okay? So the grade of the driveway was 40%. Now, if you've forgotten our whole grade discussion back in integrated 3, that is extremely steep. If you're on an interstate and you see like a 10% grade sign and they have like an angle and they've got like a truck, like a tractor trailer like on the sign sometimes and they're going down a steep incline, at 10%, those 18-wheelers are going to have a lot of trouble. So that is extremely dangerous. If you ever drive down a road that's 10%, you feel like you're falling off the edge of the earth. Like it's ridiculously steep. Okay, 40%, the cars couldn't even drive up 40%. That's how ridiculous that is. Anything greater than 30% in America is illegal. Okay, so this was an illegal driveway. If you have a Hummer or a Jeep, you can probably get up 30%. Fat chance on 40%. So the owners could not get up the driveway. The house and the driveway were built in 2002. They eventually sued the company. The company went out of business because of this major mistake of making the world's steepest driveway in history that we've ever measured. And it was illegal and it was impossible to get up. And then eventually the second owners actually bought the house at a cheap price. They moved in. 1 month later, they moved out because they were tired of parking down on the street and walking up because they couldn't get their car up the road, all right, up their own driveway. So that was a total disaster. All right, real life mathematics, you gotta love it. Okay, now you can try the homework, and you know what? We'll do like the old 80s movies where they end with a freeze frame. Let's just end this off with a freeze frame, and I'll see you next time on the evolution of Wade.